Section 7.1 deals with exponential growth functions. We're on page 478, and what we're going to do is we're going to talk about the idea of an exponential function. An exponential function is any function that's of the form f of x equals a times b to the x power. This is just a generic kind of version where a and b are going to be some real numbers. So they're elements of the real numbers. And in particular, since we're going to talk about growth in this particular section, b is going to have to be greater than 1. Okay, very important. B is greater than 1 indicates growth. In the next section, we'll talk about what happens when b is less than 1. A can be any real number. And x, or some function of x, some expression involving x, is going to be your exponent. So for example, we're talking about things that look like f of x is equal to 2 to the x power. Or let's say g of x is equal to 5 times 3 to the x minus 1 power. Is also an exponential function. Okay? It could be y equals instead of a function name equals. That's the idea. Okay? And the idea with exponential growth is as we look at our graph, as we go from left to right, this thing is either growing larger and larger in the positive direction or larger and larger in the negative direction. So really smaller and smaller, but what we're talking about is how far away it's moving, in this case from the x-axis. It's getting farther and farther away as we go from left to right. That's the idea of exponential growth. The number part of it is getting bigger and bigger. Forget the positive or negative. So let's take a look at a very simple one, such as our f of x is equal to 2 to the x power. And what we're going to do is we're going to graph this thing. Move this off to the side here. To graph this, we're just going to make a t-chart. And I'm going to plug in some points. 0, 1, 2, -1, -2. Now I just plug these or grab these points randomly, but really what you want to do is you want to focus on the exponent, and you want to figure out what value to plug in for x so that the exponent becomes 0. Well, to make the exponent 0, I just make x 0, and that's going to be my center number, and then I pick 2 points on each side of that. You don't have to do it this way, but it makes your life the easiest, in my opinion. Now, if I plug in a 2, 2 to the second power is 4. 2 to the first power is 2. 2 to the 0 power is 1. 2 to the negative first power, remember your negative exponents, that's 1 over 2, or 0.5. 2 to the negative second power is 1 over 2 squared, which is 1 over 4, or 0.25. Feel free to use your calculator to help you get these points on your t-chart. The decimal is okay because the decimal is not the final answer. The graph is the final answer. So we have our graph. Shrink it down a little bit. Move it over a little bit. So we have 2, 4. We have 1, 2. We have 0, 1. We have -1, 1/2. We have -2, 1/4. Notice if I kept going and plugged in a -3, that would be 1/8, or 0.125. Notice what's happening is these guys are getting closer and closer and closer to 0. But it's never going to get there because no matter what I plug in for x, there's no way to get an answer of 0 for y. Because if I plug in 0 for x, I don't get 0, I get 1. If I plug in positive x's, I get positive answers. If I plug in negative x's, I get fractions, but there's still positive answers. There's no way to get a 0. And what that means is that we have a horizontal asymptote at y equals 0. So this is our horizontal asymptote. Okay? The asymptote is the line that the graph gets closer and closer and closer to forever, but never actually touches. And so what your graph ends up looking like is this. And it zooms up forever. And it gets closer and closer and closer to 0 going to the left, but it never quite touches. If you were to go to where it looks like it touches, out here somewhere, and then expand it, blow it up, magnify it, you would see that there's still some gap. And that will always be the case. So this is what y equals 2 to the x, or f of x equals 2 to the x power looks like. Now, if we did something like y equals 2 to the x plus 3, then what would happen is we would add 3 to each of these. So this would now be 7, this would be 5, this would be 4, this would be 3.5, 3.25, 3.125, and we would get exactly the same thing. The only difference is that these guys would be up 3 more units. And our graph would be there. Likewise, it would cause our asymptote to also go up 3 units. It turns out that our horizontal asymptote is always going to be y equals, remember this is another name for y, equals, since this is always going to be 0 for the asymptote, this is what's going to determine whether the asymptote moves away from 0. And so in this case, our horizontal asymptote is actually going to be y equals 3. If this was a minus 5 out here, then the asymptote would be y equals negative 5. The whole thing would have moved down 5 from the x-axis. That's the idea. Now, we've talked about domain and range before. Let's talk about them again. Domain. Connect this to the x-axis and see where you end up. Well, notice that since this thing keeps going this way, and it keeps going this way, we cover the whole x-axis, which means the domain is all real numbers. That will always be the case for exponential graphs. Now, the range, we connect to the y-axis. So we connect to the y-axis going this way forever. But it doesn't go the other way forever because this piece only connects down, but it stays above our asymptote. So notice that in this case, it's always going to be y greater than 3. On our original that didn't have the plus 3, this would have been y greater than 0 because this would have been y equals 0. But this is our new version. This is our information for this one. So this is how you graph these. Doesn't matter what the function is, you're going to graph it the same way. So let's say you had something like y equals 3 times 5 to the x minus 3 power. What I would do is I would plug in, let's make this x minus 2 power. Let's make it a little less confusing, just 1, 3 in the problem. What I would do is I would use 2 as my center number. Because x minus 2, if I plug in 2 for x, the exponent becomes 0. And then I would plug in 3 and 4, 1 and 0. So 4 minus 2 is 2. 5 to the second power is 25 times 3 is 75. 3 minus 2 is 1. 5 to the first is 5 times 3 is 15. 2 minus 2 is 0. 5 to the 0 is 1. 1 times 3 is 3. 1 minus 2 is negative 1. 5 to the negative 1 is 1/5 times 5 is 3/5, or 0.6. 0 minus 2 is negative 2. That's 1 over 25 times 3. That's 3 over 25. And so this becomes 3 over 25, or 0.12. And then you would graph this thing. These are large numbers, but you get the idea, and you would have an asymptote of y equals 0, and you'd be at 1, 0.6, 0, 0.12. You'd be sitting in here, and you'd get something that looks like this. and you would see that exponential growth curve in the same way. Our domain here would be all real numbers. Our range here, our asymptote is y equals 0. We're always above it, so it's y greater than 0. Horizontal asymptote is y equals, there's nothing being added or subtracted out here from the exponential term that's all glued together, so it's y equals 0. So that's the idea of how exponential functions work. And we will start to talk about decay as the flip side of this coin in the next section.